We now start the second module of chapter 4, where we first learn the definition of diagonalizability of a linear operator and that of a matrix, and then we will introduce concepts called algebraic and geometric multiplicities of eigenvalues. With the help of these concepts, we will be able to derive criteria for diagonalizability, because it is not true that every linear operator is diagonalizable. We will see examples of linear operators which are diagonalizable and also those which are not. Let V be a finite dimensional vector space of dimension n over a field F. This is going to be our blanket assumption for this module. A linear operator T from V to V is said to be diagonalizable over F if there exists an ordered basis B for V such that the matrix representation of T with respect to the basis B is a diagonal matrix over F. A basis consisting of eigenvectors of T is called an eigenbasis for V, and the same definition for a matrix is that it is diagonalizable over F if the operator LA is a diagonalizable operator over the field F. Suppose that B consisting of the vectors V1, V2, Vn is a basis for V such that the matrix representation of T with respect to this basis is the diagonal matrix given by lambda 1 to lambda n in the principal diagonal and 0 in the off diagonal entries. Then it is clear that T of Vi is equal to lambda I Vi. Therefore, these basis vectors V1 to Vn are also eigenvectors for the operator T. The theorem which says the following: let T from V to V be a linear operator with distinct eigenvalues lambda 1 to lambda k. Suppose that V1 to Vk are eigenvectors of T corresponding to the eigenvalues lambda 1 to lambda k, then the set of vectors V1 to Vk is linearly independent. The proof is by induction on k, which is the number of distinct eigenvalues of T. If k is 1, then the vector V1, which is an eigenvector corresponding to the eigenvalue lambda 1, is obviously non-zero, and therefore the singleton V1 is linearly independent. Now suppose that k is at least 2 and that the statement is true for k minus 1 distinct eigenvalues, and obviously k minus 1 is at least 1. Let V1, V2, Vk be eigenvectors corresponding to k distinct eigenvalues lambda 1 etc. up to lambda k. Take a linear combination of V1, V2, Vk, namely A1 V1 plus A2 V2 etc. up to Ak Vk, and suppose that is the 0 vector. If we apply the operator T minus lambda ki on this linear combination, then we get T minus lambda ki of A1 V1 plus A2 V2 etc. up to Ak Vk is equal to T minus lambda ki of 0, which is the 0 vector, and the expression on the left hand side, that is T minus lambda ki of A1 V1 plus etc. up to Ak Vk, gives rise to this expression, that is A1 into lambda 1 minus lambda k V1 plus A2 into lambda 2 minus lambda k into V 2 and so on, a k minus 1 into lambda k minus 1 minus lambda k into V k minus 1, and this sum is equal to the 0 vector. Now, we can apply our induction hypothesis on the eigenvectors V 1, V 2 up to V k minus 1, because they are eigenvectors corresponding to the distinct eigenvalues lambda 1, lambda 2 up to lambda k minus 1, and then we get a 1 into lambda 1 minus lambda k, a 2 into lambda 2 minus lambda k and so on, a k minus 1 into lambda k minus 1 minus lambda k, all these are 0, and therefore, a 1, a 2 and up to a k minus 1, they are all 0, because lambda I minus lambda k is not 0 for every I in between 1 and k minus 1. Why? Because lambda 1, lambda 2 and etcetera up to lambda k are all distinct eigenvalues. Therefore, a k V k is the 0 vector, but V k being an eigenvector, it is not 0, and therefore, a k is 0. We have proved that all the coefficients a 1, a 2 up to a k are 0, and therefore, the vectors V 1, V 2 etcetera up to V k, they form a linearly independent set of vectors. A corollary to the previous theorem. So, suppose that T from V to V is a linear operator on the vector space V, which is a finite dimensional vector space of dimension n over the field F. If T has n distinct eigenvalues, then T is diagonalizable. So, this gives us the first sufficient criteria for diagonalizability. The proof is simple enough. Suppose that lambda 1 etcetera up to lambda n are distinct eigenvalues of T. If V 1, V 2 etcetera up to V n are eigenvectors corresponding to lambda 1, lambda 2 up to lambda n respectively, then we know that V 1, V 2, V n are linearly independent by the previous theorem. Then it has to be a basis for V, because V is an n-dimensional vector space. This proves that we have a basis for the vector space V consisting of eigenvectors of T. Therefore, T is diagonalizable over the field F. An example, let T from R2 to R2 be the linear operator given by T of x y is equal to x plus y comma 2y. Then with respect to the standard basis of R2, the matrix representation of T is the 2 cross 2 matrix given by the first row 1 1 and the second row 0 2. And the characteristic polynomial of T is chi T of T is determinant of T b minus T I 2, that is determinant of the 2 cross 2 matrix given by 1 minus T 1 in the first row and 0 2 minus T in the second row, and the determinant is 1 minus T multiplied by 2 minus T. Therefore, T has exactly two distinct eigenvalues, namely 1 and 2, hence T is diagonalizable by the previous corollary. The theorem, let T from V to V be a linear operator on the vector space V of dimension n over the field F. If T is diagonalizable over F, then the characteristic polynomial splits in F, that is, the characteristic polynomial chi t of t can be written as C multiplied by t minus lambda 1 multiplied by t minus lambda 2 and so on up to t minus lambda n, where C, lambda 1, lambda 2 etcetera up to lambda n are scalars in the field F. In other words, a necessary condition for diagonalizability over F is that all the eigenvalues of t belong to the field F. We have already seen a sufficient criteria, and now we see the first necessary criteria for diagonalizability of a linear operator on a finite dimensional vector space V. Proof: given that T is diagonalizable over F, there exists an eigenbasis B for V such that the matrix representation of T with respect to the eigenbasis B is the diagonal matrix with diagonal entries lambda 1, lambda 2 etcetera up to lambda n. And therefore, the characteristic polynomial of T would be determinant of the diagonal matrix lambda 1 minus t etcetera up to lambda n minus t, which is the product of these linear polynomials in T, that is lambda 1 minus t into lambda 2 minus t and so on up to lambda n minus t, which is minus 1 raised to n t minus lambda 1 into t minus lambda 2 etcetera up to t minus lambda n. So, we see that the characteristic polynomial of the operator T, which is chi t, we know that that is a polynomial of degree n, and here we see that under the condition of diagonalizability of the operator T, the characteristic polynomial factors into linear factors over the field F, and this is what is called splitting, or we say that the characteristic polynomial splits in the field F. This gives us a necessary criteria for diagonalizability. We know that an eigenvalue is a root of the characteristic polynomial of an operator T, and therefore, T minus lambda, if lambda is the eigenvalue, then T minus lambda is a factor of the characteristic polynomial. Now, the factor, if it appears k times, then k will be called the algebraic multiplicity of the eigenvalue lambda. But there is another notion called the geometric multiplicity of an eigenvalue. We will define geometric multiplicity, and we will be able to derive a criteria for diagonalizability in terms of algebraic and geometric multiplicities of an eigenvalue. Let us now define the algebraic multiplicity and the geometric multiplicity of an eigenvalue lambda of a linear operator T. So, T is a linear operator on an n-dimensional vector space V over the field F, and lambda is an eigenvalue. Chi t denotes the characteristic polynomial of T. The algebraic multiplicity of the eigenvalue lambda is the largest positive integer m, such that t minus lambda raised to m is a factor of the characteristic polynomial chi t. Lambda is an eigenvalue, therefore, it is a 0 of the characteristic polynomial, that means chi t of lambda is 0, and the multiplicity of lambda decides what would be a factor of chi t. What does that mean? If the multiplicity of the 0 is m, then t minus lambda raised to m is a factor of chi t, and that multiplicity is what we call the algebraic multiplicity of the eigenvalue lambda. Now, the geometric multiplicity. Consider the linear operator t minus lambda I on V and look at its kernel, usually denoted by n suffix lambda. This is what we call the eigenspace of t corresponding to the eigenvalue lambda. Now, n lambda is a subspace of the vector space V, and V is finite dimensional. Therefore, n lambda is also finite dimensional, and the dimension of n lambda is what is called the geometric multiplicity of the eigenvalue lambda. Now, a theorem which compares algebraic and geometric multiplicities of an eigenvalue. It says that if t is a linear operator on V, V is finite dimensional and lambda is an eigenvalue of t with algebraic and geometric multiplicities m and d respectively, then d is at least 1 and at most m, that is 1 less than or equal to d less than or equal to m. Proof: we know that d is the geometric multiplicity of lambda, that is, it is the dimension of the eigenspace n lambda, which is kernel of t minus lambda I. N lambda is a subspace of V. So, if we choose a basis V1, V2, Vd for n lambda, then we know that it can be extended to a basis of the whole vector space V, and let us call that basis V1 and so on up to Vd, and then Vd plus 1 and so on up to Vn. N is the dimension of the vector space V. We know that T of Vi is lambda Vi for every I in between 1 and d. Therefore, if we look at the matrix representation of the operator T with respect to this basis B, then in block form it looks like the following, that is, top left corner you see lambda ID, and then B and C are two matrices of suitable sizes, and 0 is the 0 matrix. So, that lambda is of course the eigenvalue lambda, and that top left block is coming from the basis vectors V1, V2, Vd. Remember that we have taken an ordered basis, and the ordering is that V1, V2, Vd appear first, followed by Vd plus 1 and so on up to Vn. Let us calculate the characteristic polynomial chi t, that is determinant of A minus T I n, and that is determinant of this matrix in the block form, that is lambda minus T I d and B in the first row, and then 0 and C minus T I n minus d in the second row. And then you see that this determinant is nothing but lambda minus t whole raised to d multiplied by gt, where gt is a polynomial with coefficients from the field f. And where does this gt come from? This gt is nothing but the determinant of the matrix C minus T I n minus d. Therefore, lambda minus t whole raised to d is a factor of the characteristic polynomial chi t, and therefore D has to be less than or equal to. Let us look at an example. Consider the vector space R2x, which is the collection of all polynomials with real coefficients whose degree is at most 2, and look at the differential operator T given by T of f is equal to f dash. If we take the standard basis B, which is 1x x square for the vector space R2x, then the matrix representation of T with respect to this basis B is the 3 cross 3 matrix with first row 0 1 0, second row 0 0 2 and the third row 0 0 0. Therefore, the characteristic polynomial for T turns out to be chi T of T is equal to minus T cube, and clearly 0 is the only eigenvalue of T. Therefore, the algebraic multiplicity of 0 is 3, and the geometric multiplicity of 0 is the number given by dimension of curve T, that is dimension of the subspace containing all those polynomials f(x) whose derivative is 0, and therefore these polynomials have to be the constant polynomials, so the dimension is 1. So, we see that the geometric multiplicity of this eigenvalue 0 is 1, which is strictly less than the algebraic multiplicity, which is 3. Therefore, T is not diagonalizable, since there is no basis for V consisting of eigenvectors of T. One more example. Let T be the operator on R3 given by T of A1, A2, A3 is equal to A1 plus A3, comma A1 plus A2 plus A3, comma A1 plus A3. It is written in the column matrix form. Now, we determine the eigenspace of T corresponding to each eigenvalue. If we choose the standard basis B for R3, then the matrix representation of T with respect to the standard basis is given by this matrix A, which is a 3 cross 3 matrix whose first row is 1 0 1, second row is 1 1 1 and the third row is 1 0 1. Therefore, the characteristic polynomial chi T of T is minus T multiplied by T minus 1 multiplied by T minus 3. Therefore, T has 3 distinct eigenvalues, namely 0, 1 and 3, and therefore, by a previous theorem that we proved, it is diagonalizable. Let us actually calculate an eigenbasis. So, there would be 3 eigenspaces for 3 distinct eigenvalues 0, 1 and 3. So, let us look at the first one, the eigenspace n0, that is the eigenspace for the eigenvalue 0, and we know what that is the kernel of the operator T, that is kernel of A. In other words, it is the collection of all those 3 tuples x, y, z such that x plus y plus z is equal to 0 and x plus z is equal to 0. So, x, y, z satisfy the simultaneous linear equations, and if we solve, then we see that it is a collection of all those 3 tuples which are of the form x 0 minus x. So, 1 0 minus 1 is surely a basis for the eigenspace n0. Is the kernel of A minus I, and it turns out that it is the collection of all those 3 tuples x, y, z such that they satisfy the system of equations z equal to 0, x plus z equal to 0 and x equal to 0. And therefore, a basis for n1 is just this singleton, the vector 0 1 0. And finally, the eigenspace n2 corresponding to the eigenvalue 2, that is kernel of A minus 2i, and which is nothing but the collection of all those 3 tuples x, y, z such that they satisfy the simultaneous linear equations minus x plus z equal to 0, x minus y plus z is equal to 0 and x minus z is equal to 0. And therefore, a basis for n2 is a singleton again consisting of this vector 1, 2, 1. We have introduced the notions of algebraic and geometric multiplicities of eigenvalues of a linear operator T. We have seen some examples also. Algebraic multiplicity is nothing but the number of times the factor T minus lambda occurs in the characteristic polynomial, whereas the geometric multiplicity is the dimension of the eigenspace in lambda corresponding to the eigenvalue lambda. And we have seen relation between algebraic and geometric multiplicities. In the next module, we will see necessary and sufficient criteria in terms of algebraic and geometric multiplicities. And what is interesting is that it is indeed computable. So, given a linear operator, if we can write down the matrix with respect to some basis of the vector space, then we will be able to compute rank by elementary row operations, and this will give us a method for testing whether an operator is diagonalizable or not.